All right, welcome back. We're going to do financial models today, and this formula right here is for compound interest. Okay, so like I mentioned, Einstein, I believe, called it the compound interest, the eighth wonder of the world, because it grows exponentially. Exponentially. So if you want to be rich, you listen up today. This is our simple interest formula. Interest is the principal times the rate times the time. I'll talk about that one in yellow in just a second. This is when interest is just calculated once, and then the interest is added to the principal, and the formula is repeated again. In fact, let's do. Let me do this first one here with simple interest right here. This second one. If a person borrows $5,100 and after 3 months pays off the loan in the amount of 5227.5, what per annum rate of interest was charged? Okay, so the amount they paid off, so you have principal plus whatever they paid in interest. And remember, interest is the principal times the rate times the time. Okay, and they so let's do this first. Let's first of all, what interest rate? Well, we don't know the interest rate yet, but we do know that they had a $5,100 principal that they were paying on times our time. Now our time is in years. So in this case, they paid it off after 3 months. So 3 months out of 12 months is 0.25 of a year, right? That's 1/4 of a year, so 0.25. So you got 5,100 times, let's see what that is, times 0.25 times R. And it looks like you got 1275 R. Okay, so that's what I'm going to put over here. So you got the amount they paid off after that time period was 5227.50. They initially borrowed 5,100, and the interest was 5,100 times 1/4 of a year, 0.25 times R. So that ends up being that 1275 R that we had, right? 1275 R. So let's go ahead and solve for R, and we'll find our interest rate here. So looks like we got 127.5 equals 1275 R divided by 1275, both sides. Divided by 1275, and it looks like we get, what's that, 0.1? Yeah, that's 0.1. 0.10, in other words, 10%, right? 10/100ths, which is 10%. All right, let's do, how about this one instead, where we have, this scenario, we have $300 is invested at 12% compounded monthly. Okay, so $300 invested. This will be our P. That's the principal we put in. And we're going to use the compound interest formula. Here's our interest rate, 12%. So 0.12. There's our interest rate. It's compounded monthly. So here's how many times. What's the compoundings per year? Well, it's 12 times per year because it's monthly. So our N is 12 is what that's telling us. And we're going to do this for 1.5 years. So T is 1.5. Find the amount. So we're going to solve for the amount at the end. How much do we have at the end? So we're solving for A. How much do we have at the end? If I put $300 in as my principal, 1 plus the interest rate, 0.12, divided by how many compoundings per year? So N is 12. N is 12. There's an N up there as well. And our time T in years is 1.5, 1.5 years. Okay. So we're going to go ahead and multiply. Let's go 12 times 1.5 would give us 18. And of course, we got 0.12 divided by 12 on the inside, which is 0.01. 1 plus 0.01. So again, please excuse my dear Aunt Sally. So we're going to do the parentheses first inside. Now we'll take it to the 18th. So 1.01 to the 18th power gives us 1.196147476, blah, blah, blah. This keeps going, but that's all it displays on my calculator. And then I'll multiply that by 300, and that'll give me 358.8442427. And we're working with dollars and cents, so we're going to round it to the nearest cent. So 0.84. That's how much money we have at the end. If I put $300 in at 12% for a year and a half, compounded monthly. Let's go ahead and make sure that we can punch that into Desmos together. So we did 12 times 1.5. That's the power, right? So it's to that power. And then we did inside the parentheses, we had 1 plus 0.01, 0.12, I'm sorry, 12% divided by 12 compounding. That gives us the 1.01 that's on the inside. So we had the 1.01 to the 18th power, and then we multiply it by 300. So 300 times, I can just click on answer, and it brings that whole thing down, because I don't want to round it till the very, very end. You want to keep this whole thing, because this thing keeps going. I'll use that answer key. Now, the nice thing about Desmos is it'll do it order of operations correctly for you. So if you put in 300 and 1 plus 0.12 divided by 12 to the, and then you put all this in parentheses, 12 times 1.5, and guess what? It'll do it for you in the order that it should. So that's the nice thing about that. And I will say, before we move on into continuous compounding, you guys, I would be amiss if I did not mention, we don't deal much with this formula, but this is for if you put a payment in, like every month type of deal. This is the compounding on that. So like, let's say you make a payment. Let's say you really sacrifice and you're like, I'm going to put in $500 a month. And I'm going to put it in, and I'm going to put it in something that tracks the stock market, and which averages 10%. Okay. And it compounds monthly for you. So N is 12. And I'm going to have it roll for like 30 years. How much money would I have if I did this? And the R over N on the bottom there would also be 0.10 divided by 12. Okay. So if I punch that in, first thing is I would do that 0.10 divided by 12. Then I add it to 1. So I got 1.0083 repeated to the 360th power. So I take it to the 360th power, which is 19.83739937 minus 1. And so now I got 500 times 18.837, blah, blah, blah. And then I divide that all divided by that 0.1 divided by 12. And that gives you 1.130 million 243.96. That's the amount you have for $500 a month for 30 years. That, my friends, is how you get rich. That's the magic of compound interest, because this money does not grow linearly. The money grows exponentially. That's a big deal. So all of a sudden, initially, yeah, maybe 10 years, you'll be frustrated because it looks like it's linear, right? But then it starts kicking in, and you really start seeing that growth as it grows exponentially, right? That's the magic of compound interest. So now, if you take that compound interest formula that we had, so it was this was our compound interest formula, and if you run this to infinity, this is, I know this is a little calculus notation for a minute, but I let n get increasingly large. That's what this is saying. Run it to infinity, right? So instead of like 12 compoundings per year, you go to like daily, right? Let n be 365. And then now let's do it, instead of just daily, let's do it every hour. So 365 times 12, so 4380. Anyways, this keeps getting bigger, bigger, bigger as we shoot to infinity. That's called continuous compounding, and you're left with this simple formula: A equals PE to the RT. So if you hear those words, continuous, compounded continuously, you got to use this formula. Automatically use this formula. It's still the principal that you put in, $300 in this case. I'm putting $300 in. Is still interest, 12%. Put it in as a decimal, 0.12, and then for this whatever time. In this case, it's 1.5 years. So we're going to go 0.12 times 1.5 gives us 0.18, and then I'm going to go e to that 0.18. If I can find my e key. And so I get 1.197217, blah, blah, blah. And then I multiply by 300. And I get $359 and 0.1652089. So $359.17 for continual compounding, continuous compounding. Okay? All right, what about determine the rate that represents a better deal? What about 9% compounded quarterly, compounded quarterly 4 times a year? Or is it a better deal to do 9.25%, a little bit higher interest rate, right? This interest rate is 0.09. Or what if you do 0.0925, 9.25, 0.0925? But it's compounded annually, 1. So which one's a better deal? Well, let's go ahead and do both scenarios. So let's say we just, we'll assume, and we'll put numbers in. We'll assume that we put in $1,000 and we'll just do it for a year. And now tell us which one's a better deal, right? So let's do scenario 1. This is the 9% compounded continuously. So let's go ahead and write the compound interest formula again. This is compound interest formula is when you put money in one time and you just let it sit there, right? You just let it sit there. So we're putting $1,000 in, 0.09 divided by 4 times a year. I'm doing it for 1 year, and let's see what we get. Pull it up on decimals. $1,000 in. $1,093.083. So 1,093.08. That's the scenario 1. All right, let's do this other one. Scenario 2, 9.25%. Still putting $1,000 in. 0.0925 divided by compounded once per year. It only compounds once per year, so the interest is kicking out once per year. We're doing it for 1 year, T time. And let's see, 0.0925 plus 1, 920. Oops, that's 0.0925 times 1,000. 1,092.50. So which one's a better deal? It's like, even though it's a little bit lower interest rate, to have it compound quarterly, little bit better deal in this scenario, right? Well, let's look at the effective interest rate. This is the formula to find the effective interest rate. Okay, so here's the scenario. Suppose you have a certain amount to invest and a bank offers you to pay a certain percent annual interest compounded monthly. What's the simple interest rate? In other words, right? So sometimes they'll say the annual interest rate. So what's the simple interest rate, which is saying, like, if it was compounded annually instead of monthly, like, what's that interest rate? That's what it's saying. That's what the effective interest rate is, right? Because if you're compounding, like for this scenario, if you're compounding quarterly, you're getting a little bit 4 times a year, and as it gives you more money, right? You take the quarter one interest and you add it to the principal, and then you get the quarter two, right? And it gives you a little bit more, so it's actually more than 24%. And so that's called the effective interest rate. And that's a great way to compare them. In fact, we could have done this on the last problem, is we could have just figured out the effective interest rate and compared the two. So that's another way to do that. But let's go ahead and do it here. If you have 24% compounded quarterly 4 times a year, what's your effective interest rate? R over n to the n minus 1. Here it is. So let's figure it out. 1 plus 24% compounded quarterly. N is 4. So I'm going to punch in 0.2. Let's go to decimals here. And it was 0.24 divided by 4. And then it was that answer plus 1. Answer plus, oh gosh, I'm really screwing this up. Answer plus 1, that was inside. So inside I got 1.06. And it's to the fourth power. And then it's minus 1. Oops. Answer minus 1. Answer minus 1. Okay. So 0.26. In other words, the whole thing together was 1 plus 0.24 divided by 4 to the n, which is 4. Whoops. To the n. And then minus 1. And that's the whole thing at one time. 0.26247. I think it was 6.9 anyways. That's our effective interest rate. Effective interest rate, so you know that's your 0.26, right? So 26%, move it over twice. 26.248%. Round that 7 up to 8. All right, let's do a couple more here. What rate of interest compounded annually, so we're compounding annually, is required to double an investment in 9 years? Okay, so here's our compound interest formula. And whatever we start with, our P, we're going to end up with double our P at the end. And we're trying to solve for R here. And it's compounding annually. And in 9 years, we want to compound, or to double in 9 years. So you got 1 plus R to the 9th power. All right, so what I'm going to do here first, let's solve for R. Notice if I divide by P both sides, P's gone. Right, we doubled it. So we have 1 plus R to the 9th. Now, how do you undo 9th power? Well, you got to take a 9th root, both sides. So we have 2 to the 1/9, 9th root of 2, or 2 to the 1/9 equals 1 plus R. And now I just subtract 1 on both sides. So R equals 9th root of 2, or 2 to the 1/9 minus 1. So let's punch that in. Let's see what we get. here it looks like I have a nth root, so I could do ninth root of 2 and then minus 1. So there's one way to do that. Or you can go 2 to the 1/9 minus 1. That's the other way to do that. So 0.0800597. Oh gosh, what'd I do? So I guess we could say 8.01%. So if you get 8.01% on an investment, it'll double in 9 years when it's compounded annually, right? It'll double in 9 years. All right, last scenario. What will a $90,000 house cost? Here's our P. 10 years from now, in 10 years, if the price appreciation for homes over that period averages 4%, if you got 4.04 compounded annually, it's only compounding once per year. So what would it cost A? What would it cost at the end of that time period if it's going up 4% a year? So it's a $90,000 house. I wish I could get a house for $90,000. 4% compounded annually in 10 years. Let's see what that gives us. One 133,221.9856. Of course, round that to the nearest hundredth because we're working with dollars and cents here. And that's the amount that we would have, right? Well, I hope you found compound interest interesting. Thanks so much for taking notes. See you guys next time.